So for this video, we'll be talking about prime factorization. Specifically, we'll start with what primes are, what composites are, and special numbers that are neither prime nor composite. After that, we'll discuss prime factorization and two methods in it. So the first method is the factor tree method, and the second is continuous division method. So let's start. So first, prime numbers are whole numbers greater than 1 with only two factors, 1 in itself. So when we say whole numbers, these are numbers that are counting numbers. So we have 1, 2, 3, So these are counting numbers, since when we start counting a number, we start with there's 1, there's 2, there's 3. Now when we say whole number, we add 0 to this one. So these are whole numbers. Now we deal with whole numbers greater than 1 with only two factors, 1 in itself. So the first prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, and 23. Now observe that in all of this, we have 2 times 1, we have 3 times 1, 5 times 1, 7 times 1, 11 times 1, 13 times 1, 17 times 1, 19 times 1, and 23 times 1. Now observe that in all of these examples, we can't really factor it in any other way other than this one. Or you could write 1 times 13. But aside from the rearrangement, basically this is it when we factor it. Since all of this has are not divisible by any other number except themselves. Now, if you don't believe me, let's say this one can be written as 23 over 5 times 5. Well, yeah, that is true, since this one will cancel out and will give 23. But observe that this one is not a whole number. Since we're dealing with whole numbers here, this one must be a whole number. So this one is wrong. You can't really use that. So this is really it. So these are basically prime numbers. Now, what if it is factorable into other factors aside from itself and 1? Now that one is called composite numbers. So these are numbers greater than 1 that has more than two factors. So the first numbers in it that are composite are 4, 6, 8, 9, 10, 12, 14, 15, and 16. Now observe that this one is equal to 4 times 1. But this one is also equal to 2 times 2 times 1, since 4 can be factored out as 2 times 2. Now this one isn't only 2 more factors. This is already 3 factors. Now this one is 3 times 2 times 1. Same goes for this one. 2 times 2 times 2 times 1. Observe that all of this is not only, the factors are not only itself and 1. See, since this one, 8 is equal to this 3. Now for 9, this one is 3 times 3 times 1. This one is 2 times 5 times 1. This one is equal to 2 times 2 times 3 times 1. This one is 2 times 7 times 1. This one is 3 times 5 times 1. And this one is 2 times 2 times 2 times 2 times 1. Or simply 2 raised to 4 if you want to simplify it. So now these are composite numbers. Now observe that in most of this are even. Observe that 4, 6, 8, 10, 12, 14, 16 are even. Well, the reason being is that if a number is even, then automatically by the divisibility rule by 2, they are already divisible by 2. Observe that in all of these even numbers, there is 2 out here, 2 out here, 2, 2, 2. So basically, if example, we're given an exercise to determine if a number is prime or composite. If we immediately see that the number is even, that's automatically a composite number since it has a factor of 2. So we can factor out 2 in it, and the remaining number is determined depending on that number. But note that we also still have odd numbers as composite. Like in this case, it doesn't have a factor of 2, but it has 2 factors of 3. So this one is still composite since we were able to break down 9 into 3 factors. 3 times 3 times 1. So now, just a quick note. We also have special numbers. These are numbers that are neither prime nor composite. So basically, when we say prime and composite, we know that these numbers are greater than 1. So clearly, 0 and 1 are not in this one. Since it isn't this one, these two numbers are less than or equal 1. So they are neither prime nor composite. So this is just a quick note in case in some exercises you see 0 and 1 and you are asked whether they are prime or composite. The answer is none already, since they are neither prime nor composite. So just take note of that. Now let's dive into prime factorization. So prime factorization is a process of breaking down a number into its prime factors. So similar to like what we did a while ago, we break down a number into its factors. But this time, its factors must be prime. So say if we are given the number, say if we have, what number did we use? Well, I think 18. We didn't show 18. Observe that 18 is equal to 2 times 9 times 1. But 9 can still be factored. So we have 2 times 3 times 3 times 1. Is this the prime factorization? Since these are already primes. Oops. 1 is not a prime, remember? Since 1 is a special number. So we remove that. The question is, can we remove 1? The answer is yes, since 1 is just like an identity element. Whether it's there or not, the outcome still remains, especially in multiplication. 1 can be easily removed. So this one are already all primes. So we can say that this one is already the prime factorization of 18, since 2, 3, and 3 are all primes. Question is, can we still write this better or more simple? The answer is yes, since we have 2 3's out here, we can write this as 2 times 3 squared. This one is still the same. So we can do that in prime factorization, especially when the factors are already large. Say if we have 100 2's in the factor of a number, we can simply write 2 raised to 100. So now let's dive into 2 methods that are often used in prime factorization. So the first one is the factor tree method. Basically, what we do here is the opposite in trees, since we know that in trees we start from the bottom to up. But in this case, we start at the top, going to bottom, and the last one remaining must all be primes. So say if we have 240 and we are tasked to factor it out using factor tree method. First, observe that one of the quickest factor that we know in here is 24 times 10, since it ends in 0. So we simply factor out 10 out there. Now observe that these two are still factorable. This one can be factored as 2 times 5, and this one can be factored as, say, 8 and 3. Now, this one can still be factored as 2 times 4, and 4 can still be factored as 2 times 2. Now observe that all of this are already primes. So we use these numbers to represent 240. Because basically what we did is we have broken down 240 into primes, or basically its roots, if we view it as a tree. The deepest roots that it has. So we have 240 is equal to 2 times 2 times 2, and so times 3 times 2 times 5. Rearranging it, we have 2, since there are 4 2's, we have 2 raised to 4, times 3 times 5. And this is the prime factorization of 240. So just as simple as that. Now let's move on to method 2. So method 2 is continuous division. Basically what we do is we continuously divide here primes in a number, and then accumulate all of that primes that we used to divide, as well as the remaining prime in the outcome, and we use that to represent the given number. So it's hard to explain really, but let's try to use the example a while ago and see if we arrive at the same outcome. So again, 240. So we have, in this case, we can't just divide 10 out here or 24. This must be a prime. So this one is 2. 2 divided by 240 is 120. Divided by 2 again. It's like repeated division, but it's like in a reverse symbol since we're going down. Oops. So 2 divided by 120 would give us 60. Divided by 2 would give us 30. Divided by 2 would give us 15. Divided by 3 would give us 5. No need to put another one since this is already a prime. So this is the end for division. Now, like I said a while ago, we use these primes, our accumulated primes on the left and the last one, to represent 240. So we have 240 is equal to, since there are 4 2's, we are 2 raised to 4 times 3 times 5. So if you check our outcome a while ago, it's 2 raised to 4 times 3 times 5, which is the same here. So basically, either of the two methods will work, but you can use the other one or the other one. I mean method 1 or method 2 to check whether your answer is correct or not. Just take note that in this case, all of these numbers must be primes. Since if we don't do that, then our outcome would have, say if we used 10 a while ago here, then our outcome would be 10 times some number. We still need to break this down. So basically, it's like extra step if we don't put primes immediately out here. So that's all for this video. We'll try to tackle more of these examples in the future videos, especially when we discuss LCMs and GCFs, since this method would be used in most of those problems, especially this continuous division. But on those cases, we'll try to have like 2 numbers out here. But that's for that's already for later. So again, that's all for this video.